Hello. Sorry, I just needed to turn on my volume. So my name is Coco, and I am just presenting my work that I did to complete the final assignment for Data 605. So starting off, the first request is that we set a seed, and we set a seed equal to 1, 2, 3, 4. I've done that right here. Then I went ahead and I defined a random uniform distribution, and I set that equal to uppercase X, the length of which was 10,000, the minimum 5, the maximum 15. I went ahead and I established a random normal distribution, the length of which was 10,000, the mean was 10, the standard deviation 2.89, set that equal to capital Y. Then I established the median of my random uniform distribution, set that equal to lowercase x, and the 25th percentile value of my random normal distribution, uppercase y, and set that equal to lowercase y. Then I went ahead and I did question A. So that was just find the conditional probability that a value in my random uniform distribution was greater than the median, given that a value in my random uniform distribution was greater than the 25th percentile of my random normal distribution. So I went ahead and I just found the amount of values within my random uniform distribution where both of those conditions were true. And I divided that by the length, which is just 10,000. And I set that as my numerator. And then to find my denominator, I just established the amount of values in my random uniform distribution, of which they were greater than the 25th percentile of my normal distribution, and I divided that by 10,000. And then I did the numerator over the denominator, giving me a probability of about 72.4%. Moving on, question B. My initial thought for question B, because I had defined these two distributions independently, I thought that I would just go ahead and I would just multiply the two probabilities together. I think based on following questions, I decided that instead I should find some different way to come across a probability, because it's asking about independence. And for me to just multiply those two probabilities together, that would imply independence. And based on those questions that will come, I figured maybe independence is not necessarily implied. So I just calculated all of the values in both sets, which a value in my random uniform distribution was greater than the median, than the corresponding median, and a value in my random normal distribution was greater than the 25th percentile. And I got a percentage of about 37 point. I got a percentage of 37.38. Next, for question C, the question reads, the conditional probability that a value in my random uniform distribution is greater than the median of that corresponding distribution, given that a value in my random uniform distribution is greater than the 25th percentile of my normal distribution. The code for this question C was just, it was just, I took the code for question A and I moved it to question C, and then just changed the direction of my inequality. And I got a percentage of about 27.5. Then I just needed to investigate this is what I was talking about with like independence. So I needed to investigate whether the probability in question B was equal to the probability of those two individual probabilities just multiplied with each other using a table. So in my table, I defined obviously A is the probability that I had defined up above. Then I have B, which is just the probability that a value in my random uniform distribution is less than or equal to the median, and a value in my random normal distribution was greater than the 25th percentile. C I defined to be a value, the probability that a value in my random uniform distribution was greater than the median, and the probability that a value in my random normal distribution was greater than the 25th percentile. And finally, D, I defined to be the probability that a value in my random uniform distribution was less than or equal to the median of the corresponding distribution, and the probability that a value in my random normal distribution was less than or equal to the 25th percentile. Now, if we look at this table, we see that first, I want to apologize for the display of this. I tried to look into it. I normally in LaTeX, you don't have to find like a special way to present a less than or a greater than. That's what I did, and obviously it showed up looking like this. So I'm sorry about that. I could not find a solution. But what we see is that the probability that a value in our random uniform distribution is greater than the median adds up to 50%, which makes sense. And then the corresponding the like alternative that it's less than or equal to the median is 50%. So that makes a lot of sense. And the same logic can be applied to if a value in our random normal distribution is greater than the 25th percentile. This makes so much sense because it's like, is it greater than the 25th percentile? There's a 75% chance that it is greater than the 25th percentile because it's the 25th percentile, and then the next probability being 25%. So it's less than or equal to the 25th percentile being 25%. That makes so much sense, and it adds up to 1. So what we realized from this table is the joint probability is 37.38%, and the marginal probability, so the result of like multiplying those individual probabilities of what I had talked about before, is 0.375. And so those values are close, but they're not exactly the same. Now we would just want to go ahead and check if independence holds by the Fisher exact test and the chi-squared test. So first I go ahead and I use the Fisher's test. And the Fisher's test yields a p-value of 0.5953, significantly higher than the goal of having an 0.05. And so for this reason, we cannot reject the null hypothesis, being that the two are independent. And the same exact result happens with the chi-squared test. We get the same p-value. We cannot reject the null hypothesis that the two are independent. Now, the Fisher exact test is best used on smaller sample sizes, whereas the chi-squared produces better results as the sample size increases. And so while it would make sense to use the chi-squared in this case, they both produce the same p-value result. So it might not be the best illustration of like a larger sample size being better suited for the chi-squared test because we get the same result. Now moving on to problem 2. So problem 2 asked for us to compete. So competing in this was rather difficult because the submission deadline had passed. So I could not enter. I did get a score eventually, and I'll show that to you. But I think because the deadline had passed, I wasn't allowed to submit. But I can show you my work. So here I go. I read the training CSV file of the crab's age data set. Here's a summary of the crab's data set. Here I here are just like some summary statistics on the crab's data set. Then I went ahead and I created a scatter plot, a correlation plot for 3 quantitative values in the crab's data set. Is this? Yeah, so these would be the scatter plots. Sorry, it's been a second and I've been working on data 602. So here is scatter plot. Here's a scatter plot matrix of quantitative values within this data set. So if we look here, we have shucked weight as the X value and weight as the Y value. Here we would have shucked weight as the X value, height as the Y value. Basically, in this scatter plot matrix, if a value is above or below a label, that just means that it's the X value. And if it's to the left or to the right, it just means that it's the Y value. So here I went ahead and I created a correlation matrix. After this, I created a correlation matrix. And I used weight and I used height and I used shucked weight. And here is that correlation matrix. Now, mind you, the diagonal values of a correlation matrix in this case are not very valuable, right? Because it's like getting a correlation value of 1 seems really significant, but you're seeing if like weight and weight it's the same values essentially. So then I went ahead and I checked the pairwise correlations for weight, height, and shucked weight. So the correlation for weight and height gave me a correlation value of 0.9. The correlation test for shucked weight and height gave me a correlation value of 0.86. And the correlation test for weight and shucked weight gave me a correlation value of 0.97. Now, what's important here is that all 3 variable combinations yield a p-value far less than 0.05, and none of the confidence intervals contain 0. These results let us know that there is likely a meaningful relationship to explore between all of these variable pairing relationships. Family-wise error involves a type 1 error or rejecting the null hypothesis that is actually true in the population, and I would not worry about that error here because the p-value is almost 0.